So it's not officially, strictly necessary to have the same scale on both axes. You may have, let's say, a longer unit on the x-axis, a shorter unit on the y-axis if necessary. However, when we are describing angles and we are describing curves according to the exact shape, but not in terms of functions, then we actually choose the same scale, the same unit length on both axes, on x-axis and the y-axis. Because angles matter. As soon as the scale is different on the axis, the angles are distorted. And we cannot describe our curves from the geometrical point of view, because that would be inaccurate then. So for analytic geometry, we always assume that the scale on both axes, on y-axis and x-axis, is the same. Same goes for the three-dimensional situation, but for now, just 2 dimensions. And of course, we know that the first coordinate is always read off the horizontal axis, the x-axis, and the second coordinate is the vertical coordinate read on the vertical axis. The system is named Cartesian system after the French philosopher, mathematician, logician René Descartes, whose Latin name, in the Middle Ages or even after that, the Enlightenment, the European main language of science was Latin, and so his French name, Descartes, was Latinized as Cartesius, and therefore we call the system Cartesian system of coordinates in English. And yes, there are 2 specific names more. X coordinate is called abscissa, and the Y coordinate is called the ordinate. That again comes from Latin tradition, but in general we can say X coordinate, Y coordinate, but actually you should know that abscissa and ordinate are specific names for the X coordinate and for the Y coordinate, simply so that we don't say X and Y, because sometimes we use a system of coordinates where the names of the variables are not X and Y, but something else. And then we won't say X coordinate of this point, we will say abscissa of this point, the horizontal coordinate. Okay, so that much about the introduction. Now, how do we find the equation of any curve? Usually there is also, I think, suppose we have an equation. So equation of a curve would describe all those points whose coordinates satisfy the equation. In other words, if I have a curve, any kind of curve in the 3 dimensions, it could be a circle, it could be something else. So if we have an equation for this curve, that is some equation connecting X and Y, it doesn't matter if the right-hand side is not equal to 0. Basically, if we move all the terms to the left-hand side, we can make the right-hand side equal to 0. So that's not so important, simply for the sake of being able to write something normally. And in this way, when we have an equation of a curve, it will be such an equation that only those points that are on the curve satisfy this equation, and only the points that satisfy the equation can describe any point, can be only those coordinates X and Y that satisfy this equation can in fact correspond to the curve. And so basically this equation will be true only and only those points, and all those points whose coordinates satisfy the equation, that is, the points of the curve. So there has to be a correspondence between the curve and this equation. So that would describe this equation. Now, the problem is that, of course, the main problem is how do we find an equation of a curve? How do we describe a curve without an equation, actually? So there are 2 things. One thing would be the description of this equation with the description of this curve using geometric properties only, describing it geometrically, not using coordinates, not using equations. And the other possibility of describing it is, of course, having this equation. So we need to somehow reconcile these two ways of description, described geometrically or described by an equation. Usually, when we describe it geometrically, some property is indicated. For example, all those and only those points that are at a distance 3 units from the given point, for instance, that would be a circle, of course, or all those and only those points that are equidistant from 2 given points. Equidistant means at equal distances. So we can describe this property verbally or geometrically, and then we have a problem how to express this using an equation. So we use the term locus. Locus is the set of all points, set of all points satisfying the property that we can describe differently. So we generally say the locus of all points equidistant from 2 given points is the curve, blah, 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 whatever, writing by equation, for example. So the locus simply means the set of all points that satisfy the property. The locus of all points equidistant from a certain point, that will be a circle. So we will use this term, locus as in location, but in the sense of very accurate mathematical description of that location. So the locus of all points means we know a certain property, and we mean the geometrical situation of all these points satisfying that property. Slightly different. Property is one thing, but locus is more like we are already thinking of the curve. We are already thinking of the set on the whole. So let's see the plan, how to find it. Let's have a plan. So suppose we know, well, we have the description of whatever property this curve or line must satisfy. So we say, okay, suppose, or we say, let M with coordinates x, y, that we don't know exactly any point on the curve. And then we say next, we need to write an equation of any kind that can describe this required property of the point. For example, we will have an example very soon, and we will have this plan on the next screen as well. So I will go through this one more. I'll go through this one more time, just with an example as well. So then we write an equation using that point M. Maybe it is equal distances. Maybe it is something about angles. Some kind of an equation that I can write using the point M. In many cases, it will be a vector equation, something about vectors. You will see. And then we express all the geometric quantities that we see in that equation, segment lengths, angles, and so on. Usually when we have vectors, we put the coordinates in, but we try to express it algebraically, not by writing point M with coordinates. We can use equation of circle, and you can use equation of ellipse, but you forget one thing. About half of you or more do not know what that equation of ellipse is actually. We will investigate the equation of ellipse. We will investigate the geometric properties. So we will start from the beginning because there are too many people who are not familiar with this. And so we will express all the geometric quantities using coordinates and the given quantities. And then, of course, we need to simplify that equation. And we will have examples. We will go through equations for lines, equations for the ellipse, equations for parabolas, hyperbolas, circles, and so on. Because in order to use those equations, first of all, we must know them. We must be very familiar with them. And experience tells me that, well, the analytic geometry unit test Generally, every semester, it tells me that there are too many people who do not know this. Yes, I know. I know the equation of an ellipse, but still, as I said, not everybody does. And so let's see, we have this plan, choose a random point, write an equation, express all the quantities, simplify the equation. So let's see, we have 2 points, 2, 3, and 4 minus 1. Let's suppose 1, 2, 3, 4, minus 1. So this would be, for example, point B. It's not necessary to sketch it accurately, even in the coordinates, because in principle, I could simply sketch any 2 points in the plane, plot 2 points, whatever points in the plane, in order to clarify the situation. It's not always necessary to have the system of coordinates. I am just using the system of coordinates, let's say, to put things into a better perspective, but it's not strictly necessary. So supposing we have these 2 points, and now we need to find the locus, that is the geometrical placement of all points equidistant from the 2 points, that is at the same distance from the 2 points. So for example, we could have a point, let's say, remember we said, let's choose any point on this locus, and let's say let it be M with coordinates x, y. So the geometric property is the distance from M to A is equal to the distance from M to B. And of course, we can imagine many points like that. But in principle, let's say M is just any one of those points. It doesn't have certain coordinates. We simply denote it by M. And then we can say the equidistant, write an equation with the required property. So we could say probably the distance from A to M is the same as the distance from B to M. AM is BM, and how will we find it? Well, evidently we could, for example, simply say, okay, the vector lengths are the same. The vectors themselves are not the same. The vectors themselves are not the same, but their lengths will be the same. So we have to work a little bit. The vector AM is evidently, let's see the coordinates, endpoint minus starting point. So it is x minus 2 and y minus 3. And the vector BM will be endpoint M coordinates minus starting point B coordinates will be x minus 4 and y minus -1, that is y plus 1. And now we have to write an equation stating that the magnitudes, the lengths of these two vectors are the same. So formally, I should be writing the coordinates of the vector AM squared and added, remember, the magnitude of a vector. The magnitude of a vector is the square root of the sum of the squares of its coordinates. And similarly, the magnitude of BM will be first coordinate squared plus second coordinate squared added, and then taking the square root. So this is basically, we have now written the equation. That was this part. This was the writing of the equation. Now we have expressed all the quantities that were involved using the given coordinates and the coordinates of the point M. And now we have to simplify this. So simplifying means, evidently, let's square both sides. And if we square both sides, then we get simply x minus 2 squared, y minus 2 squared, this is a minus, equals x minus 4 squared plus y plus 1 squared. Is it simple? No, it's not. Let's open the squares. X squared minus 4x plus 4 plus y squared minus 6y plus 9. I would expect you to know these basic formulas, really. This is from the 7th grade. You should know them. X squared minus 8x plus 16 plus y squared plus 2y plus 1. And now we see subtract x squared from both sides, subtract y squared from both sides. Now let us move minus 4x. Let's move minus 8x to the left-hand side. We have plus 4x. We have minus 6x. Let's move minus 8x to the right-hand side. We get plus 2y. And on the right-hand side, we could have, let's say, this is 17, and this is 13. 17 minus 13 is 4. Or we can write 2x plus y is 2. Or even, if you like, y is minus 2x plus 2. No, something wrong? No. Something went wrong with the signs. Sorry. Minus, and there's plus, and there's minus, and there's minus. Plus, okay. Minus 6y plus minus 6y, and minus 2y is minus 8. Sorry about that. So we can actually divide by 4. Okay, that's my fault. So this was a minus. This was a minus. Okay, so now we divide by 4. We have x minus 2y equals 1. Or if you want to write it as a function, y equals half x. Half x minus 1/2, which is not perhaps the best, but we might recognize this an equation of a straight line. This is a straight line, and so we can in fact imagine many points on this line. But basically, we could actually also mark the midpoint of the segment AB and understand that this is that line. This is that line. This is that line. So this is actually the perpendicular bisector of the segment. All points that are equidistant from two given points lie on the perpendicular bisector of the segment. So you see the segment AB. It's this one, the segment AB. We bisected. The midpoint also is equidistant from both ends. And this is actually a right angle there. The perpendicular bisector of the segment. So all points that are equidistant from two given points actually lie on the perpendicular bisector of the segment, connecting those 2 points. That's from school geometry. That should be known from school geometry in principle. Maybe you have forgotten. So if I have 2 points and I want to find all the locus of all the possible points that are equidistant from these two, for which distance to A and to B is the same, those points lie on the perpendicular bisector of the segment. That is, the line is perpendicular to the segment and bisects it exactly. So cuts it in half. So that would be one example of how we manage things in analytic geometry. What is the method? What is the way of finding the equation of a curve in a general way, perhaps? So for that, of course, we need to have some base, some starting moments. We need to have some points that are given, perhaps, some properties, and yes, we have to understand how to describe them. Okay, next, now exercises, simple ones. How do we check whether the points lie on the curve? This is simply about understanding. The meaning of the equation of a curve. Remember, the equation of a curve only works for the points that lie on this curve, and not for any other points. So basically, we have to take the coordinates of these 2 points, check those coordinates in the given equation, and see whether this is true or not. If we can put the coordinates of a point, remember that first one is x and second one is y, into the equation, and we get a true equality, then the point does lie on the curve. If not, then not. So for the point A, I would say y is 4, and we need to check, minus, and x cubed, that's minus 1 cubed. And in fact, we see that on the right-hand side, we get 5 minus negative 1, it's 6. So the answer is no, the point A does not lie on the curve. And for the point B, we see y value is 13, and we need to check if it is equal to 5 minus x cubed, and x is minus 2. So we see 13 on one side, on the other side we have 5 minus negative 8, that is, both sides are indeed equal, so we say yes. In other words, the point A does not lie on this curve, and the point B does lie on this curve. So this is simply checking. Sometimes you do need to check, but basically this is a simple exercise to make you understand how the equation is connected to the curve it actually describes. All right, next one, intersection points of the curve given and the coordinate axis. How do we do that? How do we find those? So this is the x-axis and this is the y-axis. So what do we do? Let's remember, on the x-axis, the coordinates of all points on the x-axis, y is 0. So let us put y equals to 0 in this equation, and we will have x squared plus 5x minus 6 is 0. And so we have 2x values. What are those? Those would be, if you want to factorize, or even before factorizing, we would see that those x values are, okay, you can factorize if you like, x plus 6 times x minus 1, we can think. So the points are minus 6 and 1 on the x-axis. 6 and minus 1 on the x-axis, please be careful. Minus 6. Okay, minus 6 and 1 on the x-axis. Okay, it's not to scale, definitely, not to scale, but negative 6. Negative 6, please note the signs, And now, with the y-axis, we know that on y-axis, x equals 0. So we can now put x equals 0 in the original equation and see y squared minus y minus 6 is 0. If we want to factorize, now the factorization would be y minus 3 times y plus 2 is 0. So the values of the zeros are 3 and minus 2. Not zeros, but the value, the y-intercepts. So it would be 3 and it would be minus 2. So these 4 points, so the first 2 points on the x-axis have coordinates minus 6, 0, and 1, 0 on the x-axis. On the y-axis, the first coordinate is 0, and y is 3. First coordinate 0, and y is minus 2. So find the intersection points means you have to give both coordinates. So this would be the answer for the x-axis and for the y-axis. So the sketching was not exactly strictly necessary. So we might just guess what kind of a curve it could be. So maybe some of you know what kind of curve this is. Described by this kind of equation. Well, I can tell you this is actually a circle. This is actually a circle. But in order to figure out what the radius is and what the coordinates of the center are, we would need to do some extra work. So we are not doing it right now. We will get to the circles soon enough. Just need to discuss straight lines and then we'll move on to circles, most probably next week. So I can actually tell you that this would be a circle and the center is, all right, the center is at minus 2.5, 0.1, somewhere here. So the center would be somewhere here, approximately. But that remains to be proved. Okay, rather wobbly circle, but my purpose was not to do an accurate picture, simply to give you an idea of what's to come. Okay, let's move on. Now a lot of equations, 12 equations. What loci are given by these equations? And so what locus is given by the equation? First one, x minus y equals 0.
It's a line.
It's a line. It's a line. We can see that the first equation can be rewritten as x equals y or y equals x. We know that it is the bisector of the first and third quadrant. Of course, x, y. I put a lot of small systems of coordinates so that we can actually understand and sketch. Number 2, x minus 3 equals 0. X minus 3 equals 0. Again, y is not even mentioned. That means for all y values, x has to be equal to 3. Yes?
I think it's a straight line where x is equal to 3.
Yeah, but what does it mean? Straight line, how do I sketch it? So x equals 3. Okay, x is 3. Okay, so now what we do is, of course, for all y values, x is 3, it means, okay, it means the line is vertical. Okay, poor sketch. But this is number 2, x equals 3 for all values of y, so a vertical line. And what about number 3, y plus 2 is 0?
It will be a horizontal line where y is minus 2.
Yeah, minus 2, and the horizontal line, y is minus 2. It's important to understand when the line is horizontal and when the line is vertical. Not very difficult, but simply, well, the revision needs to be done. X equals 0.
It's y-axis.
It will be the y-axis.
Yes, thank you. It is the y-axis, indeed. So on the y-axis, x is 0. And similarly, of course, y is 0 on the x-axis. Yeah. So y is 0. This is x. This is 1. Okay. Now 6. X squared minus 4 is 0.
I think it's a quadratic. So I think it will be like a parabola or a hyperbola.
Well, the problem is that there's no y. You know that the equation of a parabola or hyperbola involves y as well because it's a two-dimensional curve. So in this case, we see for all y values, we see that x squared equals 4. That is, x is positive or negative 2, which means it is a pair of lines. It is okay, now I will sketch it. Now I need to sketch it there. Let's get to this. So, okay, let me find the correct point and then I will go along. Okay, I will do. No, it doesn't. It doesn't work well. One vertical line, second vertical line, 2, and -2. So, and this one, this absolutely crooked line needs to be eliminated. Okay, 2 parallel lines, a pair of parallel lines, because we see that for all x values, for all y values, x is either +2, that would be this line, or -2, that would be this line. So basically, the locus of points described by this equation, number 6, is actually a pair of lines. We can use points on one line or points on the other line, and the 2 lines actually satisfy the equation number 6. Now, number 7.
It's a circle with the center in the origin and the diameter. And the radius is 3 units.
Yes, exactly. So again, you might not be, people might not be familiar with all circles, but certainly the circle with the center at origin should be familiar to you, because that's definitely school material. So this is a circle. We might remember from school that the equation of a circle, if the center is at the origin, is x squared plus y squared equals radius squared. So we recognize this as an equation of a circle. Now let's go on to the next one. That is number 8. Yes.
It could be like this as well. That's how it was derived.
Yes, but of course that's in general. That's the general equation for a circle. In this case, if we put the coordinates of the center, we get the simpler thing. The thing is that in general, what we see is
एशिया में तभी तो पढ़ाई सबसे टॉप पे तभी तो साले हाकी भी नासर नुसर ही है ना वेट क्या कर रही है मेरे ख्याल से
Can I continue now? If you're not talking to me, then please switch off your microphone. If we put the coordinates of the center in the general equation, we will get exactly this. Generally, in most schools, they stop at this. Let's say at the secondary education, they don't always give the general equation of the circle. Definitely, yes, we will do the general equation of a circle. Okay.
I've missed the 2 there.
Okay, now let's go on. 8. What about 8? It is x squared minus y squared equals 0. It could be many things, but let's try to keep things simple. Let's say y squared has to be equal to x squared, which means we have 2 possibilities. Y can be positive, y can be the same as x, or it can be the opposite to x. If 2 numbers are the same, the squares are the same, and at the same time, if the 2 numbers are opposite, x and y are opposite, then their squares also will be the same. So we have 2 options, y is x or y is minus x. This means we have, again, a pair of lines, but in this case, they will not be parallel, they will be intersecting lines. So any point on either of these 2 lines will satisfy this equation, because if y equals x, then the squares are equal, and if y equals minus x, the squares of x and y are again equal. So in this case, we see that we have an equation that seems to be quadratic, second order equation, but if we work with it very carefully, we actually get a pair of lines. In 9, something worth considering. So there are always these interesting tricks. So in 9, so where should I put 9? I will put 9 in this system here. Okay, in 9, we can factorize x times x plus y equals 0. So we have two possibilities. This equation will be true either if x is 0 and no matter what y is. So one possibility would be x is 0 and that is the y-axis. And the second possibility, x plus y is 0. That means y is minus x. That would be this line. That would be this line. So we have a pair of intersecting lines. In number 9, the answer is the locus is two intersecting lines, consists of two intersecting lines. One of them is the y-axis, and the other one is the bisector of the second and fourth quadrant. Y equals minus x. Number 10.
Miss, for number 10, I have a question, right? So I know it's a circle, but I'm not really sure about the radius. How? Because it will be -1, right? And how are you going to square root of -1?
Okay. So the thing is, yes, exactly. So first of all, you will in fact be able to learn about square roots of -1 in the next semester. In the second semester, there is one short topic about imaginary and complex numbers. That's true. So what happens here is we have x squared plus y squared equals -1. This is simply impossible. You cannot find any real numbers x and y such that they would satisfy this equation. So in other words, this equation does not describe any locus. So, actually, yes, locus is singular. And loci is plural. That's the beauty of the English language from Latin. Okay, so actually, number 10 does not describe any locus. The set of points is empty. It's the empty set. There's no such point. There's no such point that would fit this equation. This curve, such a curve is impossible. So this equation simply does not describe anything. 11. So we would say it's a circle with radius 0. So what's a circle with radius 0? That's just the point. That's the origin only. Because there's only one possibility when x squared plus y squared can be 0. And that is if both x and y are 0. Because otherwise, if, for example, x is not 0, then y squared has to be negative. Impossible. If y is not equal to 0, then x squared should be negative. Again, it's impossible. So the only possibility is both x and y are 0. That is a point. So the locus of number 11 is only one point, and it's the origin. And finally, number 12, I would say this is something similar to number 6. So y squared equals 1 in number 12. Y squared equals 1, so y is positive or negative 1. That would be a pair of two horizontal lines. A union of two horizontal lines. So the locus of all points consists of two parallel horizontal lines. All right, now we are moving on. More exercises. It's not all, it's not everything. So, all right, the curve whose all points are equidistant from a given point, well, I can actually give you that point 1, 3. All right, this will be 1, and this will be 1, 2, 3. So this is the point A. This is the point A. And from the y-axis, So what we see, points that have the same distance from A and from the y-axis, we can try to find some such points. One would evidently be exactly between, probably. Then another point, let's see, remember the distance from a point to the line is found by a perpendicular. Distance from, let's say, point M to the y-axis is found as the length of this perpendicular. And the distance from M to A is this. So this is one such point where the distance to the y-axis and to the point A is the same. Now we could try to find something else. Let's see, something that's evidently, clearly by fumbling around. So let's suppose this point, we can also say that these two distances to A and the perpendicular distance to the axis is the same. For this point, evidently, if it's exactly in the middle between the axis and point A, then again it is equidistant from the axis and the point. So now, evidently, this is not a straight line. Can we say this is a circle? Can we say for sure this is something else? That's not so certain. So let's simply describe this property. So the distance from M to A, or from A to M, so the distance AM has to be equal to, the distance from M to the y-axis is evidently x-coordinate. The x-coordinate is this distance, the x-coordinate of point M. And yes, we have to write x-coordinate, x absolute value at the moment, because if x is negative, we don't exactly know what happens if the point is to the left of the y-axis. So at the moment, I am writing x absolute value, x modulus. Afterwards, we will figure out how things are. And now AM, we know that the vector AM has coordinates x minus 1 and y minus 3, the differences of the coordinates of the endpoint and starting point. So end xy minus start 1, 3. And so now we can write the square root, that would be the length of AM, square root of x minus 1 square plus y minus 3 square has to be equal to absolute value of x. Now to simplify, we need to square both sides. So I will already also open the parentheses, square both sides, and at the same time open the brackets. Okay, y squared minus 6y plus 9 equals x squared. In this case, we don't actually need the absolute value anymore because the square will be positive anyway. Now we see we can subtract x squared from both sides. And so we get something like minus 2x plus 1 plus y squared minus 6y plus 9 equals 0. So perhaps I can move minus 2x to the other side and write 2x is y minus 3 square. I'm leaving it as a square, and plus 1. So these remain here, and minus 2 was moved to the other side, and of course that made it plus 2x. So we can say x is 1/2 of y minus 3 squared plus 1/2. What does this look like? If we had x and y switched, we would have a classical parabola, a classical quadratic function. In this case, it's again, we can imagine that this is a parabola, this is an equation. This is a parabola because we have x equals, in general, x equals y squared. Yes, there are some numbers added, some numbers multiplied, but in principle, it is x equals y squared. So we can think that we actually have a parabola which is placed horizontally, not vertically. So again, this is the way we will get the equation of parabola in general. So this is something that we will have to remember when we discuss parabolas further in analytic geometry, further in this unit. So this is an example of how we get an equation for a parabola, but we will consider it more specifically, the equations of parabolas, a bit later on. So we still consider the distances. We say, okay, the distance of the point M to the point A has to be the same as from M to the y-axis. And after transformation, we get this equation. So because we know that the equation y equals x squared from school, that's a parabola, we say that if we switch x and y, and maybe add some constants or divide by some constants, we actually have the general form of parabola familiar from school, more or less. So we can say, we can be fairly certain that this is a parabola. Now next, circle, center and radius given, and then writing points that lie on the circle. At this moment, I would like to start from scratch. That is, supposing we do not know the general equation of a circle, how do we get it? How can we get it in principle? How is it possible? Where do we get it as such? Okay, a little bit of a mess. Now it's going to be better. Okay, now back to pen. All right, so 1 minus 2. Let's suppose we have 1, we have minus 2. So this is the center C, 1 minus 2. And the radius is 2. So yes, we can imagine the circle goes like this, probably. We can imagine approximately what it looks like. We can even sketch it, but now we need the equation. So let's suppose that the point M is any point on the circle. Any point on the circle. So we know that a circle is the locus of all points equidistant from the center. In other words, we need to find all the points for which the distance from C to M, or the length of the vector CM, equals 3, 2. The radius is 2. So, of course, again, the vector CM has coordinates as we are already used to it. Just a moment. Okay. X minus 1, y plus 2. Those are the coordinates of the vector CM. Now we can find the magnitude, the length of the vector, x minus 1 squared plus y plus 2 squared equals 2. And simply squaring both sides, we get x minus 1 squared plus y plus 2 squared equals 2 squared. So now what happened here? We are not simplifying this. What happens here, we see that the center has coordinates, for example, in general, if the center has coordinates, for example, x0, y0, then in principle, what happened here, this is subtracting x0, this is subtracting y0. So in principle, we have x minus x0 squared plus y minus y0 squared, and this 2 came from the radius. So actually this 4 is radius squared. And in principle, we already have the equation of circle in general. This is the general equation of any circle with center x0, y0, and radius simply r. So in principle, when we discuss circles, probably next week, we will not look at how do we find the equation. We already know how we find the equation. We did it with specific numbers here, the very concrete, very specific circle, but we understand that if we simply put the coordinates of the center and radius in general, instead of these numbers, 1 minus 2, 2, we get the equation of the circle in the general form. And this is the general equation of a circle. So it gives you immediately from such an equation, you can see the coordinates of the center and you can see the radius. So this is a very good equation in that sense, because you only have to look at it and you already know where the center is and what the radius is. We can do it with a specific circle, as we did in this case, or we can make it in general. Now, what about the points? M1, M2, M3. Does M1 belong to the circle? Does it lie on the circle? We simply try its coordinates in there. So we have 1 minus 1 with 0 square plus 2 square equals 2 square. So it looks like yes, the answer is yes, because you can put the coordinates of M1 into this equation and get a true equality. Minus 1 minus 3, minus 1 minus 3. If I put minus 1 here, I have 2 square. And if I put minus 3 here, I get 1 square. So no, point M2 does not lie on the circle. And 3 minus 2 would give us 2 square plus 0 square is 2 square. Then point M3 would again lie on this circle. 3 minus 2, that would be actually this point. That would be this point on the circle. Minus 1, minus 3, that would be somewhere here. And we see that, no, it would not. It would be outside the circle. We can even imagine where it looks, where it lies in the system of coordinates. And 1, 0, that's this point, the point of tangency. So now we see how we can also check points for the circle. We can also use this equation to determine whether a point lies inside or outside the circle. All we have to do is see whether the square of the distance from the center, the left-hand side, is greater than 4 or less than 4. That would be again something that we can use such an equation for. Next.
Miss, I have a question regarding question, right? So, Miss, since they asked for the equation of the circle, do we need to expand the equation?
Okay, no. When you obtain an equation, this is actually the best form for this equation because you see the necessary parameters of the circle.
Yes, right. Yeah.
Sometimes you might need to expand, but more often you have to go backwards from the expansion by completing the squares, getting this form. That's more useful, actually.
Okay.
This is more useful because if it's expanded, like the one in the previous somewhere.
Yeah, I know what you mean.
This one. You have to go back because in this case, you have to go back. I think you wrote it already that you can find the center. So that's the whole point. This form is actually the canonical form is the best. Okay, 2 times closer to A than to B. What's that? Minus 1, 1. That would be point A. And minus 4, 1, 2, 3. This is minus 4. And 1, 2, 3. This is 4. That would be this point would be B. And this is A, for example. So in this case, you need to find the equation for the locus of all points that are 2 times closer to A than to B. Okay, one thing could be, evidently, one point would be this. I will again make them in a different color. Okay. 1 point would be this, 2 times closer to A than to B, evidently. Then 2 times closer to A than to B. Another point could be, for example, this. Is it a straight line? How do we know? 2 times closer to A than to B. Let's see, can we go there? 2, and that's the distance somewhere there. Looks like, possibly. So the distance to A from the point M, x, y, 2 times closer to A than to B. This means, in principle, that if we compare the lengths of the vectors AM and BM, the lengths of these two vectors, the vector AM is 2 times shorter than the vector from B to M. In other words, BM length is 2 times vector AM length. So this is where we have to be careful and put 2 in the correct place. So BM is 2 times longer than AM. And now, once again, we deal with the coordinates. So vector AM would be x plus 1, y minus 1. And vector BM would be x plus 4, y minus 4. And now we write the magnitude. So 2 square roots of magnitude of A, x plus 1 square plus y minus 1 square equals magnitude of BM, x plus 4 square under the radical, of course, y minus 4 square under the radical. Now, when we square both sides, please remember that when we square 2, it becomes 4. And of course, it gets multiplied by each of these squares. So x squared plus 2x plus 1 plus y squared minus 2y plus 1 in parentheses, because it's multiplied by 2 square. We also have to square the number 2. And on the right-hand side, we have x squared plus 8x plus 8 plus y squared minus 8y plus, not 8, 16. 16. And now we have to open these. We have to open these parentheses, and so we have 4x squared plus 8x plus 8 plus 4y squared minus 8y plus, not 8, this was 4. Oh, sorry. I keep writing things that are not true. This was a 4. Plus 4, and this is 4, and this is x squared plus 8x plus 16 plus y squared minus 8y plus 16 again. Now we see that 8x and 8x disappear. Minus 8y on this side, minus 8y on that side disappears. And so when we put things together, moving to the left-hand side, 4x squared minus x squared is 3x squared. 4y squared minus the y squared is simply 3y squared. And on the right-hand side, we have 16 and 16, that's 32. And then we have 4 and 4, that's 8. 32 minus 8, that's 24. And so dividing both sides by 3, we have x squared plus y squared equals 8. This is interesting. We get a circle, and the center of the circle is not even between the point B and A. The center of this circle is at the origin, so it would be, as we now see, something like this. The center would be at the origin. And it turns out that at all points of this circle, all the points on this circle are 2 times closer to A than to B, in a very interesting fashion. So this is a very interesting way of describing a circle. This is something quite interesting. Points 2 times closer to point A than to point B. It's a circle. So one might wonder what other kind of equations of this kind would give us a circle, or maybe some other curves. Now, next. Now, more exercises. As you can see, a curve is given by parametric equations. Parametric equations means that we still are dealing with a figure, with a curve in the plane, but in this case, we are not determining x in terms of y or y in terms of x. We are not writing as a general regular formula or as a regular function. However, we will deal with parametric functions as well. So what this means is that we can change the value of parameter t. So t is called the parameter. T is called the parameter. So in principle, as t increases or decreases, as t changes, x and y of course change too. We still consider in the plane y to be dependent on x, so they being, let's say, codependent perhaps. But the change is described by changing the value of the parameter. And so points corresponding to the t values. All right, t, and then here we will have points with coordinates. So t, 1 minus 2 to 0. That's 0. If t is 1, then we have the point 1, 0. Simply putting the parameter 1 into both equations at the same time. That's imperative, that we put the same value of t in both. Minus 2, we have t squared is 4, and minus 2 minus 1, y value is minus 3. If t is 2, we have a point 4, and 2 minus 1, 1. If t is 0, we have the point 0 and minus 1. So for each value of parameter t, we have a point, and for each point, we have a value of parameter t, or sometimes it could be more than one parameter t, if the curve actually intersects itself, and we could get the same point by using 2 different values of parameter, that's possible. And the equation of this curve in the form, let's say classical form, that is, get rid of parameter. How do we get rid of parameter? We take the equation which uses the parameter in the simplest form. That is, we could write t equals y plus 1 and simply put it into the first equation then. So x is y plus 1 squared, or if you like, x minus y plus 1 squared equals 0, if we really need the 0 on the right-hand side. We can write it like this. And once again, we can say this looks like a parabola. This should be a parabola. This should be a parabola because x is expressed using y squared.
Miss.
Yes.
Miss, I want to know in our course there will be a will there be a question with where the parameter of the equation will be cos theta and sin theta?
We will have a little bit of patience. We will have everything. There you go. You wanted this. So x is cosine of t and y is 2 sine of t. Again, t values are given, and let's find some points, and then let's work with this equation. So if t is pi half and minus pi and 2 pi and 0. Then the point, let's say xy, would be cosine of pi half is 0, sine of pi half is 1, but times 2, we get coordinate 2. Minus pi, cosine of minus pi is minus 1, sine of minus pi is 0, multiplied by 2, still 0. 2 pi, when t is 2 pi, the cosine is 1, and the sine is 0 again. And if we have a 0, we have the same situation. Cosine is 1 and sine is 0. So we see that actually we return to the same point at some moment. Now, how do we write the equation of this curve in terms of x and y only? Now here...
Yes, I think we could use the trigonometric identity.
Yes, that would be a good idea.
Then which is cos theta plus sine theta equal to 1, and
yes, that's the thing. Because otherwise we would need to express t using arc cosine of x. That's not pleasant, really. That's really unpleasant. So we will not use inverse trigonometric functions, but we just remember that sine square of t plus cosine square of t equals 1 for any values of t. Whatever t is, no matter what we think, no matter what we want, whatever t value is, the sum of the squares of sine and cosine is 1. So all we have to do is, of course, express the sine using y and cosine using x. So we would say, evidently, y divided by 2 is sine. So the square plus cosine is exactly x squared equals 1. Or we could say x squared plus y squared divided by 4 equals 1. This is an equation of an ellipse. At the moment, I'm not giving you a very general equation of an ellipse, but you can imagine what's going on here. We see that the y coordinate seems to be sort of squished. Well, actually, this ellipse is going to be vertical. This ellipse is going to look, as we will see later, somewhat like this. Somewhat like this, 2 times higher than its wide. That's okay. That would be a bit lower probably, but we will see when we deal with the ellipse. So this is interesting. If I didn't have the 2, if I only had cosine and sine, I would have the perfect circle. X is cosine t, y is sine t would be a circle. But because y, as you see, is stretched, it's not simply the sine t, but it's 2 times more. So the y is stretched in y direction, it seems. So even from this, we see that it seems to be, okay, if I didn't have 2, I would have a circle, as we see. But because I have 2, it's stretched 2 times vertically. That's something that we can already start considering about the ellipse. Okay, x is t cube, not very visible. I accidentally have cut the edge off. And y is t squared minus 4t plus 3. And now we have a point 3, 0, and we have to find the value of t corresponding to this point. In other words, I know that x is 3, and I know that y at the same point is 0. So now how do we deal with t? We need to find t, and just remember that value of t that we will find must fit in both equations at the same time. So one value of t for which both x and y would be what we need. Which equation is easier to use? So you might think
quadratic.
You might think the quadratic. The quadratic equation will give you 2 y values. The quadratic equation will give you two y values, and then you will have to check, not two y values, but two t values. And then you would need to check in the x to see which of the two t values works, or maybe both. That's one possibility, because the quadratic equation will have two roots. But on the other hand, the cubic equation will have one root. If we see that t cubed plus 2 equals 3, then t cubed equals 1, and t equals 1. There's only one real root. Yes, there are two complex roots, actually crazy numbers, absolutely crazy numbers that are also cube roots of 1. But in this case, in real numbers, we have only one possibility from x. So in this case, that's actually very curious. We might think quadratic is lower degree than cubic, so quadratic might be easier to use. But in this case, you see the cubic is very simple, and we can find t is 1. Then we have to check. So if x is 3, then t is 1. So actually we say if x is 3, then we see that t is 1. And then we have to check, is y equal to 0 with this? And when we put it in, y equals 1 squared minus 4 times 1 plus 3, we have 0. And then, so this is the one and only value, t is 1. Of course, we could do it the other way around. Of course, we could say, okay, what if y must be 0? Then t squared minus 4t plus 3 is 0. Solve this, we have t1 is 1 and t2 is 3. We check 1 in the first equation. So if t is 1, then 1 cubed plus 2 is 3. And if t is 3, then we would have 3 cubed plus 2. No, that's not 3. So this does not work. We can do it this way. Just remember to check. If you find more than one t value, you have to check that it fits in both equations. All right, what else do we have? Circle and this. So 2 more exercises remaining, and we have something like 13 minutes. I think we can manage them both. So circle, but parametric. And that's a big problem, because we can write in Cartesian coordinates using only x and y. We know how to write this circle, but how do we deal with the parametric equations? Okay, so that means x and y both expressed in terms of some parameter. So that would be the point C, the radius is greater than. So evidently that would be something like this. It doesn't matter what it looks like exactly. What matters is evidently we need to find some kind. So this is 2 and this is 1. So we need to find a way of writing the parametric equations. So in principle, we have discovered basically that writing parametric equations of a circle should use trigonometry, should use t. The parameter t would in this case be an angle. What kind of angle we could choose, in fact, but probably it's the best way of figuring out the angle t as the angle of rotation from the horizontal positive direction, as we generally do in trigonometry. So this would be the point xy, point M. This is the point C, and let's call this, I don't know, P. Right? And so if we say that t is the angle, so t, of course, could be anything between 0 and 2 pi, for instance, a full revolution would give us the circle. A full revolution would give us the circle. So we could say, let t be this angle Let t be this angle of rotation starting from the positive x direction around the center of the circle. And now we have to figure out how to express x and how to express y. X, that would be, let's say, at this point, we can in fact say that x is in fact 2 plus evidently CP. 2 plus evidently the length of CP. And we know that CP, the horizontal side, the horizontal leg of the triangle, the adjacent leg of the angle T can be expressed using cosine. So it would be radius times cosine using school trigonometry from the plane. If we have the angle T and if we have the radius 3, as we know, then this leg would be 3 times cosine T. That's from school trigonometry in a right triangle. So I would say plus 3 times cosine T. And if T is greater than 90 degrees, as T goes over there, if the point M rotates, then in fact we would get a negative. 3 times cosine T would be a negative number. So of course we would have subtraction, and actually the coordinate x can be less than 2, and it can be even less than 0. So this would work for x. And what about y? The y value of the point M would in principle be 1 plus the height of this triangle, the length of MP. And the length of MP is the opposite leg to the angle T. So that means it needs to be expressed using sine 3 sine T. So this is from school trigonometry or school trigonometry in right triangles. So this would be 1 plus 3 sine T. Again, let's have a look. So when sine is negative, if we rotate beyond 180 degrees or beyond the angle pi radians, the sign becomes negative. And yes, of course, the point goes below 1. That's all correct. And so we have these parametric equations. X is 2 plus 3 cosine T, and y is 1 plus 3 sine T. These would be the parametric equations of the circle. So when you need to write parametric equations for a circle, then remember that having sine, cosine is the best thing that we can have. Also, you could remember projections of a vector, because in principle, what we see here, we have projection of the vector CM, that would be CP, with a positive or negative sign. So this is actually the projection. This is the projection of the vector CM on the x-axis. And this is the projection of the vector PM on the y-axis, of the vector CM, I'm sorry, it's still the same vector, CM on the y-axis. So in principle, we could use vector projections. But in this case, using school trigonometry is also good if it helps. And finally, the last one. Parametric equations of the trajectory of a small ball thrown from a certain height horizontally with given velocity v. And we will use time as a parameter. So a little bit of physics, evidently. So what happens to a ball when we throw it horizontally from some certain height, let's call it height h0, is of course that the velocity works horizontally, it's a vector, But basically, what also works on the ball is the gravity. So what happens is, of course, the ball falls down. That much we know. So at any given point, it will be a parabola, yes, but we have to prove it. We have to demonstrate that it's going to be a parabola. So we have, let's say, coordinates x, y, but we need the parametric equations. So after a time t, let's suppose that after a time t, that ball has coordinates x, y, and let's try to figure out what these coordinates are. So the x coordinate, we are of course assuming that the air resistance is negligible, that air is not slowing it down. So after time t, if the velocity is v without air resistance, the distance traveled would be v times t. Velocity, constant velocity times t. The horizontal velocity is considered constant because we assume that the air resistance doesn't slow it down, the horizontal component. Now, what about the vertical component of the velocity? The vertical, it's time times. Now, what about the vertical component of the velocity?
So it would be the height it traveled. I mean, like it not traveled, the height, reduction in the height, changes in the height.
Wait. I need to get the eraser. It's actually, I have to subtract. I need to subtract something. Okay, so I have the height h0 minus the distance traveled vertically. What is the distance traveled vertically in time t? Now that's formula from physics, something that should be familiar from physics, and that would be gt squared divided by 2. That's the distance traveled in time t under the acceleration of gravity. And we know that g is, of course, approximately 9.8 meters per second squared. And so it's actually any distance traveled if we have acceleration a. If we have acceleration a, then the distance traveled is a t squared divided by 2. That's from physics. And yes, we can prove that this is a parabola. That is, for instance, if I express t as x divided by v, and please remember that v and g and h0, they are constants, then I can write y equals constant h minus g times x squared divided by 2v squared, which basically, again, I repeat for the last time, that this is a constant, and this is a constant, v is a constant, v squared is a constant. So in principle, I have y equals something like, c minus ax squared, where a and c are simply constants, some numbers. I'm not talking about acceleration at this moment in terms of a. So we see very clearly that, yes, indeed, it has to be a parabola. So this is let's say, not a complete proof, because what we are skipping at this moment, yes, gt would be the velocity after some time, but the distance traveled is something else, a little bit. So this is from physics. And this is something that we actually skipped. This development. This is from physics, and mostly we can work with this when we do calculus. With calculus, this is easier to find and demonstrate. So we are skipping it at the moment, because what is of more interest to me at the moment was indeed understanding the parametric equations in principle, how parametric equations work in fact and in principle. All right, so we have, 1 minute remaining. 1 minute is 1 minute. Next time, so on Wednesday, I would like to remind you that at 8:15 we will do elementary mathematics. So those who need, for the first half of elementary mathematics on Wednesday, the earlier class at 8:15, we will do some 45 or 50 minutes of new material in elementary mathematics, and then we will have elementary mathematics first test. And then you have a half an hour break, and some people will have longer breaks, some people will have a shorter break. I have posted a file with the group lists. Each group has a different Zoom link, so make sure you are on the correct page. On the correct page, you will need to open that file in order to get to the Zoom link. Because otherwise, if I put the Zoom link in the public area for everybody, there will be people who click the wrong link by all means. So make sure you open the document and click on the correct Zoom link. It's not the regular class link. In elementary mathematics, yes, it will be the regular class link, even if it's in the wrong time. But for the mathematics one, for our vectors test, it will be a new Zoom link for each group, not the lecture link. All right. I hope everybody.
I have a question regarding homework, right? So, Miss, you showed us how to draw the vectors in the 3D last week, right?
Yes.
But in the homework, so you gave us you gave us 2 points.
Yes, but you may sketch the vector starting from the origin. I am not asking you to do the 2 points. You can simply take the vector coordinates, put it at the origin.
Okay, because
at the origin. Yeah, I know. Otherwise it will be very, very difficult. I know. That's why you may put it at the origin. Yes, it will be easier.
Okay, so I could start it from the origin and draw the vector, right?
Yes,
okay,
yes,
thanks.
Exactly.
Thank you.
Ma'am, I have a doubt.
What?
Ma'am, on an elementary test, there is an MCQ or a written test.
It is pass-fail. It is pass-fail. You have to get at least 4 in order to pass. But in principle, all that matters is that you pass it.
Okay, thank you.